We present distilling on-device language models for robot planning with minimal human intervention. LLMs endow robots with contextual reasoning and a natural human interface in domains from personal assistance to mapping and exploration. However, LLM-enabled robots rely on cloud-hosted models requiring network infrastructure such as Wi-Fi, 5G, Starlink, and others. And while this works in structured environments like homes or offices, this prevents operation in environments where internet is unreliable or unavailable. We need performant on-device models, however this is not possible with existing SLMs or distillation frameworks. We address these limitations via PRISM, a framework for distilling on-device language models for robot planning that produces SLMs rivaling the performance of state-of-the-art LLMs while requiring minimal human intervention to train. PRISM takes as input an LLM-enabled planner conditioned on a task and an observation, and that produces an action. Because these inputs are textual, they can be synthesized to produce training data for SLM distillation. PRISM does this through first synthesizing scenarios comprising environments and semantically coherent tasks. PRISM then emulates partial observations via environment masking, and using these partial observations, it emulates closed-loop planning with the input LLM planner, which produces data samples of synthesized tasks, observation, action sequences. PRISM uses these data samples to construct a dataset, which it uses to distill an SLM via supervised fine-tuning. This SLM can then be deployed onto various robotic platforms and serves as a drop-in replacement for the source LLM. We evaluate PRISM on 3 distinct planners for mapping and exploration, home assistance, and manipulation. Each planner has a distinct task set, and in our experiments, we focused on distilling GPT-4o to Llama 3.2 3 billion parameter models. We provide one example where PRISM is deployed on a UAV and tasked with assessing roof damage. It correctly infers the semantic goal, that is, it needs to map a building, and then guides the UAV there, and it collects the necessary information for the user. Across all 3 planners, we find that Llama 3.2 3 billion parameters achieves only 10 to 20% of GPT-4o. However, PRISM boosts this to over 93% across all 3 planners. We then perform latency analysis, and we find that PRISM is comparable to GPT-4o in ideal network conditions. It is also robust to network dropout, unlike GPT, because it runs on board. In summary, PRISM produces effective SLM on-device planners using only synthetic data. The trained models are under 5 gigabytes in VRAM, which enables onboard planning on platforms such as UAVs and UGVs. Thanks for watching.